So I'm going through this bulletin that I'm about to go through is true in the statements for the 2022-2023 school year. They issue a new bulletin each year with some new feedback. The first comment that I want to pull from the bulletin is just about time limits. You're allowed double time, but when they write the exam, they've written it meant to be a 3-hour exam. Now, the old 3-hour time limit was a little tight for students. Okay, often you'd wish you'd have a little bit of extra time. A good goal is to not be much more than 3.5 to 4 hours. Okay, you can do the exam in 3, but you've got that a little extra time to double check and confirm stuff. If you start constantly second guessing yourself and doing everything over again, it tends to not help you. Okay? So that's my advice, plan for about 3.5 hours, about a half hour or 45 minutes of extra time unless there's a good reason to take more. Okay? The breakdown of how both your test in this course and how the diploma is written, even more so if the diploma, is the questions come from categories, thinking processes. So the very bottom of the thinking process would be your straight up memorize. What is the definition of? And you don't really get any of those questions. You will not be asked, what does reduction mean? Okay? You'd be asked to apply that. Okay? What reactant undergoes reduction in this example? When they write the diploma, about 75% of the questions are applying the knowledge that you've learned to typically one outcome. Okay? 25% of the questions are what I would call higher mental activity questions. You're applying multiple skills. Okay? Maybe you're using your knowledge of reduction chemistry and some acid-base chemistry to talk about whether the pH is going to go up or down as a reaction occurs. Higher mental activity aren't necessarily harder or longer, but it requires a much higher understanding. And if you understand the multiple concepts, you might fly through it. Okay? And it may not feel harder, but this is how your diploma is written. Okay? There's a big separation between a student above and below 80. A student above 80 is in the standard of excellence category. They're getting a high percentage of these HMA questions right. The acceptable standard is when you're above 50%. You're getting more than half of the questions in total right. Okay? So it's important to realize that. The questions aren't labeled HMA or acceptable standard. Okay? So you have to not overthink questions that might be sort of the 75% category that you should answer quickly in maybe 1 minute. Okay. So we have I've kind of commented on everything that's here, but realize the diploma is written with these two types, you know, acceptable standard, students and questions. Acceptable standard is greater than 50%. Standard of excellence is above 80. So this is a thermal question. This is, excuse me, an example of what an acceptable standard question would look like. Okay. It's a reaction with methanol. Okay. You'd have to realize the reaction. Okay. You really don't need to go about balancing it. If you look at all 4 answers, they all have the exact same reaction. Okay? So before you balance, look at the answers and see if there's any difference. Okay? There isn't a difference in how they balance it. It's always 2 methanol and 3 oxygen making 2 CO2 and 4 water vapor. So you need to be able to predict the value from your data booklet and select the right answer. Okay? So there's really just one outcome in this acceptable standard type of question. Another example of an acceptable standard question, this time it's in equilibrium. And let's go through and solve this one. Okay. So you're given a bunch of data, And then you want to jump and read the question before you read the top. So don't start reading at the top, jump to the bottom. The equilibrium constant for the reaction in the graph is, they're asking you about Kc. Okay. A lot of the time, the very top box information may not be necessary. But once you see Kc, you know you need an equilibrium law expression, and then that's sort of the key bit of information at the top. So we need an equilibrium law expression. I'm not going to write the expression. I'm going to jump into putting in the values. You'd want to start with 3 hydrogen. So you have to realize the equilibrium is where it's flattened out. So you're not using the very beginning. These would be the I values. The E's are anywhere out where they've leveled out and come to dynamic equilibrium. So 3 hydrogen. So there's hydrogen. That'd be 1.8. 1.8 cubed. You'd want to check your units are moles per liter, and they are. If they were millimoles per liter, you would have had to convert them. So that would be easy to miss. That'd be maybe kind of mean or unusual on a diploma. Then we've got carbon monoxide gas. That's 0.6. No power there. Then we have 1 methane and 1 water as reactants. So methane, 0.4, and water, 0.2. Okay. Now, I'm not going to worry too much on the diploma about significant figures because the question is going to tell me how to report this. We're asked to put our 3-digit answer. They don't mean decimal places, they just mean 3 numbers. Okay? Now you're going to have to key out where the decimal is. So when I did this on my calculator, I got 43.74. Okay. So my 3-digit answer would be 43.7. Those are my 3 digits. Okay, now when they tell you report your 3-digit answer, you're going to key out the 4, the 3, the decimal, and the 7, but the decimal is not a digit. And the answer, that is what the answer had, so I've done it correctly for this question. Continuing sort of along through the bulletin, standard of excellence is for that 80% plus, so we'll take a look at a couple standard of excellence questions. Now, teachers know what the standard of excellence questions are, and we try to prepare you really well for them. So a pretty typical standard of excellence in redox is building a reduction table. I would hope you would find this actually kind of easy. Hopefully you did it in the lab, you've done lots of practice, okay? And then the diploma will always have some sort of ordering. It'll always be build a reduction table and then order the OAs or the RAs, and they could pick highest to lowest or lowest to highest. Okay? That's the typical format. So let's try to solve this one. So let's do the decoding of the information, and then I'll pause and you can try to build the table. So one of the trends, elemental metals are always reducing agents. So that's going to kind of help you there figure out your agents fairly quickly. Okay. If you know all your OAs, the metal ions, which are typically, if you know all your RAs, the metal ions, which are typically OAs, are going to have to be. So our first reaction, lanthanum 3+ did not react with indium, so the indium on the right as an RA must be above lanthanum, which would be on the left side of a table as an OA. Next, lanthanum did react with NP. So I'm going to build right off that. I can go down to NP, okay, because we have a reaction. So the oxidizing agents are going to go on the left side of our reduction table, reducing agents on the right. NP it did react with ND3+. So I'll get that out separate. So ND3+ did react with NP. So then we're going to have to piece this together. There's NP and there's NP. Last, lanthanum elemental did not react with ND ion. So ND3+ did not react with lanthanum. And then we got to put this together. There's lanthanum, and that's kind of where lanthanum would be in that sequence. Okay. You know, pause, and then we'll put a table together shortly. Through everything. Okay. So before I build the table, I'm going to look ahead at the question. It says order from strongest to weakest the oxidizing agent. So we don't actually have to build a whole table. It's almost not worth your time being full and complete with all the electrons. Okay, but I'll certainly stick to the OA on the left, RA is on the right, and I'm going to drop the electrons because we don't need them. So what's coming out at the top? There's nothing coming out above indium. We know lanthanum, that half reaction will be below indium. The NP is going to be even lower still. Okay. Now ND is going to be above NP, but we've nothing that suggests it'll be above indium. So kind of piecing thing, indium would be our best reducing agent. Indium 3+. Okay, and I'm going to leave the electrons out because I just need an order. Okay. Then we've got lanthanum is going to come next, that half reaction. Again, it's +3 electrons. I'm not bothering because I don't need that to answer the question. Now we got to sort out NP and ND. Okay, we know NP is below lanthanum. Okay. We know ND is below lanthanum, but this tells us that the ND is above and the NP is at the very bottom. So the ND and then NP. So what is our question? Order from strongest to weakest, the oxidizing agents. So they're this column. We need to get that order out, strongest to weakest. So that's our strongest, which is 5. Then lanthanum, which is 8. ND, 7. And then finally NP is our 6, which is good. My order matches the answer key. So they take a bit of time. When you get this question, you're going to be pretty shocked not to have a table building question, and you've got to decide before you go into the exam, are you going to tackle these longer questions first, or are you going to wait and tackle these second? But I would have a plan. Same with a titration question. Hopefully you know how to do titrations, but you know it's going to take you maybe 3, 4, 5 minutes. Okay, have a plan going in. Are you doing them now, right away, or are you going to do all those simple questions that maybe you don't need a calculator and on round 2 through the diploma? So that's a standard of excellence example. A little bit more into the nuance of the exam, and then we'll get back to some more examples. Okay, so for this year, which is 5 different diplomas, the weighting of thermo is about 20 to 22. That's typical, so that's going to be about 12 questions. Electrochem, about a third, so that's going to come out to approximately 18. Again, I don't know exactly your diploma. It could swing a question. The organic is going to be about 12, and the equilibrium is going to be about 18. Now the weightings kind of swing that the 18 is more likely to be 18 or low, and the 12s are more likely to be 12 or 13. Okay. So that's your breakdown of the units. Okay. The type of questions you're going to get for every diploma this year: multiple choice is going to be 44, numeric response is going to be 16. You don't know what units it's going to come from. Okay. But that's what we'd get. And we're going to see sort of the typical numeric response type questions coming up. This is your first page. It's a little boring, but I don't want you to be surprised by anything when you crack the diploma. It's going to say 3 hours, but you know you're allowed double time. Okay? It mentions a little later you're allowed 6 hours. You definitely need an HB pencil to fill in that bubble answer sheet. Okay? You should check with your teacher whether your calculator is good. A TI-83, a TI-84 is fine. The TI Inspires, I have to double check, but I haven't seen anybody using those. Okay? Any standard scientific calculator is fine. It's only if your calculator has memory to store things that you potentially need to check, where you could be storing things that you shouldn't. Your calculator should get cleared. Okay, so don't be surprised if somebody asks to take your calculator. They would clear, if you had a matrix, anything in any graphs pre-set up, all that's going to go. It also will change your mode, but for chemistry, it doesn't matter for radians or degrees because we don't use that. Physics students have to watch that mode, degree or radian. Okay, you are allowed a ruler and a protractor. There's really no need for either. You definitely don't need a protractor, and there's no written part to do a ruler. So just, you're allowed. It's not really recommended, okay, unless you like a ruler for just organizational purposes. Okay. And that's about all that's important on the answer sheet or on your first page of your exam. Just please make sure you don't fold, bend, do anything to that answer sheet. Okay, and the writers don't have the diploma supervisors don't have backup answer sheets. Okay, so please don't spill anything on it. Some multiple choice, and particularly numeric response nuance, how to fill in the bubble sheet properly. Multiple choice, you're used to that. You're just carefully circling in the bubble. Numeric response, we've seen one example already of filling things in. Okay. They give an example of if you had to average out 3 numbers, 20.0, 21.0, 25.5, and 24.5, okay? And they ask you for the average. You don't have to think about how many digits to report. It tells you 3 digits, okay? So when you average that out, the first digit is a 2, the second digit is a 3, and then you need a decimal, and then there's a 7. So you're going to start on the far left of your answer sheet. Okay, don't start on the right. Sometimes you'll have blank bubbles. You may not always fill in all of them. So the very first column is your 2, then your 7, and there's a decimal at the top to bubble in. You know, they only put decimals in the middle of the answer sheet. Okay, that decimal doesn't count as a digit, and then you'd put in the 7. Okay, you must put in all the digits that you are requested to. Okay? In previous bulletins, they gave an example in thermodynamics where the answer was something with a decimal place. Okay? And the diploma creators explicitly tell you if you bubble in 58, okay, and do not report the last digit, even if it's a 0, you'll be marked wrong. You did not report it as intended. So if it says, you know, 3 digits and the last one's a 0, bubble in that 0. Don't drop it. Okay? Also, don't think about sig figs. Just follow what they tell you to do. Okay? It should match up with significant figures, but you don't have to worry about it. Okay? We'll see how to deal with leading zeros in a second, how Alberta Ed wants you to bubble them in. Okay? An example of if you just have 4 things that you're going to order, you're just going to bubble in those numbers. Okay, so the question is rank these 4 sciences in terms of alphabetical order, and you get 2, 4, 1, 3. So there's no commas, there's no spaces, there's no blanks, you just bubble in the 4 numbers. So that's fairly straightforward. Next question you'll see, or example of bubbling in, they ask you from 5 subjects, art, music, physics, biochem, which ones are sciences, in which case, and they tell you there's 3 answers. So you need to start on the left. Okay. And they're telling you to do 3 answers, so the most right-hand column will be left blank. Okay. So don't start on the right, make sure you start on the left. Scientific notation questions. Okay. Those often is where you'll see the A dot BC times 10 to the positive or negative D. Okay. So they ask in the left-hand question on the board to key in Faraday's constant, okay, which is 9.65 times 10 to the minus 4. And they tell you to bubble it in A dot BC, so that's your A, your B, and your C, times 10 to the negative D. It's a little hard to read on the board. So they don't want the negative, your D value is just the power. So if those scientific notations, don't put any decimals in, don't go 9.65, it's just 9.654. Is all you're going to bubble in. That's what you'll do when they say the A dot BC. If they say key in your 3-digit answer, then you are putting a decimal place in. So that's an important sort of nuance. 3-digit answer, include a decimal. A dot BC times 10 to the negative D, the decimal is not something you're keying in. You're just doing A, B, C, D. Okay. One thing that tends to show up, particularly in electrochem or organic, is questions that have multiple answers. Often the first choice is totally irrelevant, but it sets the correct answer. So an example of this, not to chem, but using countries, is use the numbers above to choose a continent, match it with a country, and match it with a city. Okay? So it doesn't matter whether you pick North America, Europe, or Asia, there's a correct sequence for all of them. Okay? So I'll pick Europe. Okay? Didn't matter that I picked 2. Okay? What's a country in Europe? France, China, or Canada? Well, that's going to be France. Okay? And then the capital city of France is going to be Paris. Okay? It's not Beijing. It's not Ottawa. So that would be 9. But that's just one of several correct answers. So I've done the middle of the 3 correct answers. Okay. You could have also went 1, 6, 8, or 3, 5, 7. Okay. So where I've seen this in the past with electrochemistry is in electrolytic cells. Okay. They might give you an electrolytic cell, they'll tell you some chemicals are in it. Okay. They'll hook up a power supply, but they won't label the polarity. Okay. And the first part will be, what is electron flow? Is electron flow 1 or 2? Okay. And they'll tell you in the question there's multiple correct answers. Okay. The first part is often irrelevant. Maybe I will pick electron flow as 1. And once I've picked 1 as my electron flow, it has to be anode to cathode. So now I've made that side my cathode, and I've made that side my anode, and now I've locked in the rest of the answers. Okay. But this could seem odd to you if you haven't seen it before, and you wouldn't have seen it from me very much. Okay. So multiple answer numeric responses. Don't get hung up on, oh, I could have picked 1 or 2. They both work. Pick one, label it carefully, write on your diploma, and then do the rest of the sequence. Examples of numeric response. So we've kind of left behind oh, sorry, we're still continuing numeric response. This is one I think we can do. So methane gas can be produced in a lab. We've got an equation. Then we've got some data. Let's figure out what we or you are about to solve. What is the concentration of hydrogen gas at equilibrium? Okay. So this is going to be a mathematical question. It's going to be an ice table type question. Okay. So with these, you're going to want to probably copy that equation onto some scrap paper or somewhere else in your exam. I'm not really giving myself quite enough space. First thing I would check is we got gas, 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 so there's no solids or pure liquids to drop. That's a good place to start, and then you can kind of get going with setting up your ice table. And we know hydrogen at equilibrium, that is the goal of this question. So I'll stop, but you can now read that box with a focus on what you care about. I'm going to transfer over the information. Hopefully you had a chance to start thinking and of reading through and realizing that's what you need to do. We've got to watch initial and equilibrium. So we've got that word initially. Initially at a temperature, I could care less about the temperature. It's not going to affect our table. 0.18 moles per liter of carbon disulfide. I tend to not fit my units right in my ice tables. 0.31. Closed container. No mention of the products. Would assume those wouldn't have any. At equilibrium, when equilibrium is established, so at equilibrium, there's 0.13 mole per liter. So now I'll leave you for another little bit to think of, okay, how are we going to get to that question mark? Don't fill in more of the table than you need to get to that question mark. Not. So with ice table questions, if you know an I and an E, that's where you want to start. If you have an I and an E, you're not going to need an X or a variable. So our change, that's dropping from basically 18 to 13, but there's a decimal place. So that's 5. Okay. Now our stoic, one of those needs 4 of those. So 4 times more hydrogen is going to react compared to the carbon disulfide. So 5 times 4 is 20, okay? But it's going to be 0.20. Okay. So we have basically 31 minus 20, but it's 0 point, and we're going to get 1, 1. Okay. And that's going to be the right answer. We got to key it in properly. We're kind of not super used to this language. It says key in your 3-digit answer. Okay. When your number is between 0 and 1, they request that you key in the 0 first. So don't bubble 0.11. That 0 is your first digit, and then the 1 and the 1. And that's really the point of this example, is to kind of see that nuance. So they're not saying significant figures. They are saying 3-digit answer. You do the 0, the decimal, the 1, and the 1. Now it matches sig figs. All our information is to 2 decimal places, and our answer is to 2 decimal places. So we're not throwing out sig figs. We're still following them. Okay. So that's probably the oddest nuance with numeric response, that leading 0. Another numeric response, hopefully you can fly through this quickly. Do you remember boiling points? Can you sort through them? Now, you've got a name here that you don't know. That alone wouldn't be fair game. but they give you the formula which makes it okay. So you don't have to know what octadecanoic acid is, but you basically just add the oct and the dec, and they show you the formula. So you should be able to answer this. So I'll pause quickly, and then we'll put up the answer in about 30 seconds. So solving these, there's a nice controlled variable. All of these have all three forces. We've got butanoic acid, methanoic acid, octanoic acid, and octadecanoic acid. They're all carboxylic acids. So they're all a tie for that hydrogen bonding and dipole-dipole. Okay? What is different is the London dispersion forces. Least electrons will have the lowest boiling point, so the smallest will have the lowest boiling point, the biggest, most electrons, highest boiling point. So what's our smallest? Well, that would be meth. Right away, we're going to meth. You're not going to get smaller than 1. So that is our second answer. Next biggest would be bute. Okay. Now we've got oct with 8, and then this octadecal with 18. So oct would be next. And then last, we have this name we haven't seen before, but you can deal with. Okay. So you're just going to key out those 4 numbers in your answer key. So your decimal would be left blank. A Venn diagram, I don't see these a lot in chemistry. I hear they're showing up in your math diploma a fair bit, okay? But it's worth talking our way through a Venn diagram. So we have acids only. We'll blow this up and shrink it a bit. So we've got acids only, we've got bases only, and then we've got the middle, which would be the overlap of acids and bases. And then before we read all those descriptors, we want to read what is the question. The characteristics and example of section 2. Okay? Read this before you go through your list. So section 2 is descriptions or examples that are both acids and bases. What terms apply? So let's go through our list. Can water be both an acid and a base? Yes. Carbonic acid. Okay. You may have to look this up. It's H2CO3, and it is not a base. So you may have to go to your acid-base table, look for it. Okay. I know it's not. It might take you longer. Sodium carbonate. There's no hydrogen in carbonate, so it is not an acid. Okay? Sodium carbonate is just a base, so that would not fit in section 2 of a Venn diagram. Sodium hydrogen carbonate, HCO3 is both on your acid table, or in the acid column and the base column. Okay? You'd call it amphiprotic. Okay? So that would fit in that overlapping acid and base. Okay? Can be diprotic. Can acids and bases both be diprotic? Gain or lose 2 H's? Yes, they can. Phosphoric acid can lose 3. Carbonate, which was a wrong answer, is a diprotic base. So the diprotic term can apply to both acids and bases. Okay? And monoprotic certainly can apply to both acids and bases. Okay? Accepts protons? Well, that's only acids. No, that's only bases. Donates protons is only acids. So we have 1, 4, 5, 6. So that's the answer, but you could put it in any order. You don't have to go 1, 4, 5, 6. You could go, You know, you might figure out 5 and 6 first, and then do 1, and then do 4. They'll all be marked correct. Okay. So don't worry about the order when it's just what is as a question. Okay. Another sort of multiple column question, and your brain wants to do them in sort of order, but the answers may not necessarily be the order that the columns are presented. So we've got some columns. It's worth scanning the headings first. So we've got organic material, we've got processes, we've got types of reaction. I haven't even read the top, and then I want to go down to the question. So propane can be recovered from organic material numbered. So what organic material would we get propane potentially from? Well, it's not those. We're not going to recover them from. You'd have to realize it's crude oil. Okay? This just came up in talking about fractional distillation in that lesson, which kind of leads to the next answer. So propane can be recovered from crude oil. That's the heart of the Alberta oil industry. That would be the oil that's pumped right out of the ground. Whatever is in the ground comes out. The word crude means it's unrefined. It hasn't been separated. It doesn't have any use until it's been refined. Okay? Then we talk about a process for separating it, and that is fractional distillation. Okay. Now, I haven't really talked explicitly about solvent extraction. We've talked about the theory. Okay. Solvent extraction would be if you want to remove something probably from the ground and you want to do it with a solvent. Okay. So if you had hexane in the ground, it's a liquid, and you wanted to extract or solvent extract this, you'd have to realize that this is LDF only, so you can't use water as a solvent to go and extract oil. It's not going to dissolve it. They're not going to mix. So if you wanted to solvent extract this, you would have to add a solvent that is LDF only. Okay. So solvent extraction is just picking a solvent that has the same forces as whatever you're trying to extract. Okay. We've done the theory, just not that word. Okay. A fractional distillation is going to come up on your diploma in some form. Okay. Propane can react with chlorine. This is kind of why we have those number 1 and number 2 answers. Propane reacts with chlorine in the presence of ultraviolet light. So that's a huge word. Your brain should be thinking substitution as soon as you see UV light. Okay. In the type of reaction numbered, substitution is 8. Okay. And anes don't do addition anyway. So you've got 2 pieces of information that tell you substitution. And the organic material numbered, to produce hydrogen chloride and what product, organic material. So when you have a ane, okay, and you do a substitution, you're still going to have an ane at the end. So it looks like it should be 1. Okay. So a bit of pieces to go through, and you kind of had to jump around the table. So we've got to get these in the right order. 3, then 5, and then 8, and then 1. So this has a big emphasis on going through sort of different formats of numeric response. It lets us pick, it lets us practice, and multiple choice, those are standard. We don't need to go through nuances of multiple choice type questions. We're soon going to be, I'm going to skip over this one for the sake of time and get to sort of the comments per unit. But I don't want to skip this one because this is a really good applying observations that we've talked about so much in labs. So let's Okay, we're not going to read the whole thing. It's worth looking at the equation. We got silver ions and copper ions, and they're telling us key stuff. They're not going to say that's colorless for no reason. But we've used silver ions. Hopefully remember that was a clear bottle. Only copper 2+ ions had a color in the lab. Okay. So clear silver reacts with copper to make silver, and copper 2+ ions, which are blue, that we've seen. Okay, so what's the question? Okay. Using the numbers above, choose one material that would cause a shift in equilibrium and then match the direction. This is really important. There is more than one correct answer. This can really get you stumped if you don't notice that. You're like, oh, you see 2 possibilities. And when you see that, you're like, yeah, there's 2 possibilities because there's at least 2 answers, and there might be 3 or 4 or 5. You don't know how many, but you know there's at least 2. So choose material. In this question, it does not matter what you pick to start with. 1, 2, 3, and 4 all lead to a correct answer. So you just have to pick one. I'll pick a hot plate, number 1. Now I've locked in one answer key and one answer key only. And you're going to help me. If this reaction is on a hot plate, what way will it shift? You can use your hands. You've got to find that energy term. It's a product, and heating it, a hot plate is going to put in more energy, so it's going to want to shift away from the heat. So backwards. So many were correct. So that's a shift towards reactants. And let's see, then we got to pick 7 or 8. Is this solution going to get lighter blue or darker blue? So as we go backwards, the blue is going to act as a reactant. It's going to fade away, and we're going to make more of a colorless solution. So the solution will turn a lighter blue. So 1, 6, 7 is one of several answers. Don't start going down the pathway of thinking of more than one answer. I think that's a dangerous pathway to go down. Pick what you think is the easiest. Okay? So you've got heating, you've got cooling, you've got adding sodium chloride, which is a little trickier because you'd have to remember chloride is going to precipitate silver or remove it. So that's what's going on with the answer with 3. With 4, you're just adding silver ions. Okay? Make your life as easy as possible. Now, it may not be the same. You may remember one of these circumstances from a lab and be more comfortable. Okay. So that's all the questions that I have to go through. Now we just got some important comments in the bulletin. I'm not pulling them all out, but I would take these to heart as guessing questions, and they're areas where students have made mistakes in the past, and you don't want to make those mistakes that Alberta Ed says your peers last year made. Okay? So some trends. Okay? Now I've hopefully prepared you not to make these. Okay? In thermodynamics, some students just always pick water, but make sure you read the question. You've practiced with aluminum cans and factoring that in. A lot of diplomas now, to sort of test students to make sure they know to think about the chemical, might have the heat go into an aluminum block, okay, or an iron block. And you can look up any material on page 3 of your data booklet that is given to you. So don't just 4.19 because that's what you use 95% of the time. Okay, so their students are not catching this when they put it in. Okay. Now, I've talked so many times about the middle yellow bit. If you have an open system with water, you get water vapor, and if you have a closed system, you get water liquid. So I would hope my classes do not make that mistake. Okay. But it is a semi-common mistake. What I do see as an issue, even in my classes, is what's in red. students, however, students have more difficulty relating these enthalpies to bond breaking and bond forming. So this is talking about chemical potential energy diagrams, reaction coordinate, potential energy. Breaking bonds requires energy to be put in. Forming new bonds is the down. I'm just going to make sure this is clearly exothermic. It's in my notes, but again, my students make errors with this, they forget. Okay, you have to, my analogy to help remember this is magnets. Okay, magnets that are originally stuck together or bonds that are together, you need energy to rip them apart. You have to put energy in and you see the potential go up. Magnets that are apart spontaneously snap back together and you get a release of energy when new bonds are formed or when magnets spontaneously snap back together. So I hope the yellow isn't an issue. The red might be something that you've forgotten about. Now, I don't see the red on all diplomas, but that's the warning from this slide. Okay. So in electrochem, what is Alberta Ed sort of warning us to watch out for? Okay. And you've seen this on tests. Students are pretty good when things are in your reduction table. Okay. Even if it's buried in a reaction, students pull out the half reactions. But when half reactions aren't in your table, students aren't super successful at writing half. So I have a full redox reaction, and let's write a half from this. Okay. I'm going to figure out the reducing agent half reaction as an example of what students in Alberta tend to struggle with. Now I'm going to do this together, and then I'm going to have you do the half once I've identified the reducing agent. So we have dichromate and ethanol reacting. Okay, just looking, we don't know which one is which agent. You can't guess. So what is our strategy? That would be oxidation numbers to try to figure out what our agents are. So I'm going to put in the oxidation numbers fairly quickly. O is 2 minus, and anything that isn't a peroxide. And then dichromate ends up being plus 6. The two of them plus 12, which, and then we have minus 14 for the 7 O's, and that leads to our charge. Our ethanol, hydrogens are always plus 1, all 5 of them, and then the 6th one there. Oxygen is minus 2. So that carbon needs to be minus 2. The 2 of them would be minus 4, and then the O would be minus 6, and then the 5 H's would balance that out as plus 6. Okay. Dichromate, well, its oxidation number is just its charge. And then we got carbon dioxide, minus 2 for each of the O's. 2 of them would be minus 4, so this is plus 4. Okay, so I'm asking to get the reduction, the reducing agent half reaction, so we've got to find what's being reduced. Let's start with the dichromate, and I'll pause once I highlight the numbers. We're going 6 to 3. So that's a 3 electron exchange for every chromium ion, or atom, sorry. But is that gaining or losing? You know, pause. So plus 6 down to plus 3. So if you're +6 and gain an electron, you'd be +5. Then you gain another one +4, you gain another one +3. As you gain something negative, the charge would go down. So gaining electrons reduced. So we've actually found our OA. This would be our RA, and it's not in our table. So we're /U are going to write the reduction half reaction. We've got that ethanol becoming, well, if we follow the carbon, we've got the carbon at the beginning and it has to turn into CO2. So let's see if you remember how to balance a complex half reaction. So just wrote out a little reminder of our sequence: atoms other than O and H, then O with water, H with H+, and then we balance the charge with electrons. So other than O and H is just carbon. So 2 carbons at the beginning, we need 2 carbons at the end. That's kind of science 10-ish. Now we've got to do O with water, and we've got O in a few places. We have one O at the beginning, 2 pairs at the end, which is 4. So 1 versus 4, that's a 3 difference, and we need to add 3 waters at the beginning. Now there's 4 O's at the beginning, there's 4 O's at the end. Next, hydrogen, and there's a bunch of them at the beginning, none at the end. We've got 5 and 1, 6 green H's, and then 3 times 2, 6 red H's. So 6 green, 6 red, 12 H's at the beginning, so we need 12 H+ at the end. Last, we need to add electrons. This isn't too bad because we've got a neutral molecule and 3 neutral molecules, so there's no charge at all at the beginning. At the end, we've got a neutral carbon dioxide, and the only charge is 12 H+, plus 12. So this is the product side is the high side, and we need 12 electrons to bring it down to 0, which is the low side. We finished our list, so that is the correct reduction half reaction. And in this course, we only deal with acidic or neutral half reactions. We never have to worry about anything being basic, even though they are in some textbooks and in some worksheets. They're not accessible. So this would be borderline an HMA type question. You had to apply multiple skills to get through this. Okay. Moving to the end. Okay. So we're into our 3rd unit, sort of key comments that I've pulled out. Okay. Organic chemistry is 3 sections. Okay. We've got the naming and classifying that I would hope you do very well at. Then we've got the physical properties section, which students across the province tend to struggle at a little bit. And then we've got the reactions, which really come down to, do you memorize and get comfortable with the reactions or not? You can be highly successful with these, but it tends to be a bit binary. Okay. So I think you kind of know what to expect. You're not going to be shocked when you see a fractional distillation question, and that's what I really emphasize. They don't put solvent extraction on very often, which is why I didn't talk about it really at all. I talked about the theory of solubility, not that technique specifically. Solvent extraction shows up as a wrong answer a lot. you see fractional distillation and solvent extraction as two possible answers. And 9 times out of 10, they'll ask about fractional distillation. Okay. So I want to keep going. Really not a lot on organic to highlight, other than make sure you know your reactions. Equilibrium. I've got a couple slides in equilibrium. Would have highlighted, Alberta Ed says students struggle, my students sometimes struggle with implied stresses, not explicit, you heated it up. You put it on a hot plate, that's kind of explicit. It's the removes that you might struggle with. So if you see a question where they add sodium hydroxide, but there's no sodium or hydroxide, you'd have to realize that that can remove H+. That's acid-base chemistry. Okay. Now the next removal I talk about all the time, and you've seen it in at least one or multiple labs. Okay. If you have silver ions, which are aqueous, and you add chloride ions, you can do that as a dropper. Okay. And you're going to remove those silver ions, you're going to precipitate them out, and they're going to fall to the bottom of your solution as a solid. My subscript S didn't come out. Okay. Those are the two that you're most likely to see on a diploma. But in theory, anything from your solubility table on page 6 could show up, or that's the basis of the precipitation. Okay. Silver and chloride on page 6, you would predict a precipitate. Okay. So that's the one main thing I want to highlight from that paragraph. Okay. Next is a little just bit on variables. I've said this orally a lot in the lab. I haven't written it out. When you're talking about controlled variables, you can only put the variables down that you have control over them. Okay? So when you're designing an experiment, if you choose to keep concentration the same, okay, you do a corrosion lab, you do 1 mole per liter of hydrochloric acid, 1 mole per liter of sodium hydroxide, you had control over that. It's a controlled variable. Okay? You can control the volume. Okay? It's not a controlled variable if you did not have power over it. Okay? So don't put those things down, and students regularly make that error. They want to put things down that they don't have any control over. It just happens to be the same. Something we burned food items, and it helped us address thermal efficiency. So I hope you do reasonably well, much better than the province, on efficiency of calorimetry. Okay. We've talked about things like if you put a heat shield around the burner, you're going to increase your efficiency, you're going to lose less energy. You've got to watch the height between the flame and your can. Okay. If it's too high, you're going to, or if it's high, the higher it is, the lower your efficiency will probably be. Okay. Students tend to struggle with this. I would hope our class would not, and students from our school. Another bullet, one that I maybe wouldn't expect, on your diploma, if they talk about corrosion and it's open to the atmosphere, the bulletin's reminding you that there's going to be water and oxygen present there. So this is Alberta, where it's pretty dry and unhumid, okay? But there's always some humidity or moisture in the air. You've got oxygen out in the air, so factor that into possible corrosion reactions. Okay. I don't see this all the time. I'm a little surprised it's in the bulletin, but it's there, so we kind of can't ignore it. Okay. I would expect this to come up in one of the 5 diplomas this year. Okay. The November, the January, the April, the June, or the August, or multiples. I already mentioned this in that balancing question we did a couple minutes ago. That was an acidic balancing. You don't have to do basic ones, though they show up again in workbooks, and they're in the Nelson Chemistry 30 textbook. Glassware. Okay. Labs are so important. You've done labs. You've been building skills from Chem 20 to Chem 30. Okay. Anytime you do volumetric analysis, those would be your titrations, whether it's Chem 20 or Chem 30. You do titrations because you want to very precisely know the concentration of some solution. And that's when we stop using graduated cylinders. Okay, we use devices that give more significant figures. You use a burette for the titration, and for the sample, you're going to use a pipette. So if you have a question about glassware and it is a titration, you can't pick graduated cylinder for your sample. That is not an appropriate glassware choice. It's what you've done for every lab in 20 and 30. You use those pipettes. Okay? The pipettes, most of the time we use the 10 mil, and they're 10.00 mils. 4 sig figs. Okay? We don't always need that many sig figs. Okay? But in titration analysis, volumetric analysis, we do want those. Burettes also give us 2 decimal places, and we can have 4 sig figs when you do V final minus V initial. Okay. You should be able to identify the glassware also. A little bit more electrochem. They're just highlighting what I mentioned with the anode always being on the left in cell notation and the cathode being on the right. That's how your diploma is going to be. They will stick to that convention for electrolytic cells. Okay. So voltaic, you've got the double line to separate the 2 half cells. In electrolytic, you don't have the double line, but they're going to keep the anode on the left, and the cathode on the right. In voltaic cells, it's super useful because it tells us the copper from the silver, which is which electrode. Okay? But in electrolytic, it often doesn't help us. Okay? We've got 2 inert carbon electrodes in my bottom, or in the Alberta Ed bottom example. So knowing the one on the left is a anode doesn't help us. Okay? But that's the formatting they'll stick to. Okay, cell notation, anode to cathode, either type of cell. We've talked a lot about observations. A lot of students in the province struggle with making observations, and they highlight, okay, you should be able to know whether the pH goes up or down. You should know color changes. That's page 11 in your data booklet. Color changes of the electrodes. Mass changes, whether an electrode is going to get heavier or lighter. And color changes right near the electrode as opposed to throughout the whole solution. So this is the same example that I did the RA half reaction from, but we could talk about observations we might see if this was run inside a cell. Okay. So you might need to grab your data booklet, look at this, and we'll talk about observations shortly. Let's kind of work through this together, sort of chemical by chemical. So the first thing we have is dichromate. So we want to think, what could we potentially see from dichromate? That's an aqueous ion, so it's in solution. Okay. So there might be a color to it, and page 11 would tell us the color, and that is orange. But it's a reactant, so over time, what's going to happen to that color? That orange would fade away. Now, the lower the concentration, the lighter the color would start. So dichromate, color to be decreasing. Ethanol, we have no information in our booklets on ethanol. We've used it in the lab. It is a clear solution. So there's nothing we can get from ethanol. So that's not going to help us for observations. If we looked at our first product, we've got chromium 3+ ions, and they're on page 11. So chromium-3 is a blue-green at 1 mole per liter, or green when it's 100 times less strong. So at 1 mole per liter will be a blue-green, but we wouldn't have any color to start with. This blue-green color would be forming or increasing as the reaction occurs. So we'd see green first at lower concentration, and then eventually some light blue, maybe if a mole per liter was made. Last, we have carbon dioxide. Our booklet isn't going to help us, but we would see something. We would see bubbles. Okay, if you form carbon dioxide. Okay. So there is no pH change at all. There's no H plus or OH minus being formed. So the pH would be 7 and it would just stay 7. Okay. There's no electrodes or solid metals mentioned here, so there's no mass change that could show up in a diploma question. A few things, again, a bunch of these I'm going to fly through. I've really stressed hydrocarbons are C and H only. Watch that term. The bulletin is warning you of this. Hydrocarbon derivatives, they're going to have the halogens, X. Okay. Fluorine, chlorine, bromine, iodine. You see one of those atoms, you have a hydrocarbon derivative. So watch that. If they say, identify the hydrocarbons, you can include organic halides on that list. Okay. Now, the aromatics that are just C's and H's would fit as a hydrocarbon. This slide's about saturated and unsaturated. And the way I've said it, I think, has prepared you well. It's in terms of the carbon, and is it filled with as much hydrogen as possible. Okay. A double bond outside of the carbon-carbon chain doesn't make something unsaturated. So if we have a hydrocarbon chain and it's filled with hydrogen, okay, a double bond, but not between the carbons, doesn't affect whether something is saturated or not. Okay. Those 4 carbon to carbon, those 4 carbons with 3 carbon to carbon bonds have no doubles or triples. The carbon piece is filled with as much hydrogen as it could. There's no enes or ynes. Okay. Don't look at other double bonds. Okay. And this is kind of a warning, not necessarily to my class, but to students. Just look at the carbon-carbon bonds for saturated or not. Okay. Okay. They explicitly talk about propanoic acid. Okay. Okay. Those 3 C's are all connected by single bonds, so it is saturated. We've got a concept that if you have an ene and you add bromine or chlorine to it, if you have an ene, you're going to turn that into an ane with no catalyst. Okay. If you have an ane and you add bromine, nothing's going to happen without a catalyst. Okay. Now this is calling this type of setup the bromine test. Okay. It's been a test on your unit test. I've talked about this several times, and I've mentioned it shows up in most diplomas, and a lot of students get this wrong. Okay. So this is really making sure you understand addition reactions versus substitution. The substitution needs a catalyst where addition does not. Okay. Substitution can happen, but it's super slow without a catalyst because you need sort of UV light getting through a window or some light coming from some source. Okay. So that's the bromine test. So hopefully on the diploma, if you get this, you're going to be successful with that. You've seen it a few times. I'm going to skip right over. This next bullet is really the same theme I just talked about. If you have double bonds, bromine's going to react with it. I haven't really talked about potassium permanganate. It's been in your workbook, but that also will react with double bonds. It works the same as the bromine test. So you add bromine to an E-9, the yellow bromine is going to fade away as it reacts. Okay. You use potassium permanganate. It's that beautiful purple color that looks like Kool-Aid. Okay. That also reacts with double bonds. So if something is unsaturated, it does the exact same thing as bromine. So the yellow we've talked about, the red underline I have not. So potassium permanganate reacts with double and triple bonds. Comment about, you know that there's two types of substitution reactions. Alberta Ed never mentions dehydrohalogenation and dehydration. So you don't need to know those terms, but you need to know there are two different types of reactions. There's different catalysts or reaction conditions. Okay? And you've been tested on that. Okay? So hopefully you'll outperform the province on that. Okay? A really nice bullet, we're going back to equilibrium now and talking about ways to change the pressure. We've done this, but not in one section. So how can you change the pressure? One way is by playing with volume. We're used to that. If you want the pressure to go up, the volume needs to go down. You can make predictions there. Okay. The very bottom, I've highlighted it in red. If you add in a reactant or product gas, that would change the pressure. Okay? But I color this red because we would just think of this as a concentration change. That's how I've taught you to deal with it. But I want to emphasize, it's been mentioned, but I don't talk about it a lot. It shows up in most diplomas. If you have an inert gas, so if you pump some argon into a gas reaction, if there was, 1 million molecules per liter of oxygen before, and you pump in some argon, there's still 1 million molecules per liter after. Adding an inert gas does not change any of the pressures, the individual pressures. We call them partial pressures of any of the gases. So if you add an inert gas, there's no shift. I know that's in your notes. We don't talk about it a bit, but it's probably going to be somewhere in your diploma. Okay. Sometimes students infer, if you add a gas, it drives the pressure up. It's kind of true, but it doesn't change the pressure of any of the individual reactants or products. So it has no effect. So this whole slide is really summarizing inert gases have no effect, or gases that aren't part of the reaction have no effect. Everything else we've well covered. Students struggle, including some of mine, with terms mono, poly, and amphi. You've got to make sure you can keep those separate. It really makes a nice theory question. You may want to look at your acid-base table. I want to talk about the terms that would be true for H2PO4. Okay. Now, H2PO4, okay, I'm not writing reactions. I'm kind of doing a little bit of a flow chart, can lose an H and become HPO4 2 minus, and that H can be lost to become PO4 3 minus. So that red species can lose 2 H's. Both of those are in your acid-base table. Going the other way, it can gain a third H and become neutral, and we never see it gaining a fourth H. Now, realizing it can gain 1 or lose 2, lets us use a lot of the key terms to explain this. Okay. It can gain or lose, so this is an amphiprotic species. I'm just going to use amphi. It can gain, it can lose. As an acid, is it mono or di? Or kind of mono or poly? So acids would be losing H's, proton donors, Bronsted-Lowry theory, and it can lose, it can go 2 to 1 or 1 down to 0. It can lose 2 H's. So this is a diprotic or polyprotic acid. As a base, that'd be going to the left. That's a proton acceptor. It can only accept 1. So this is a monoprotic base. Being able to keep this clear on an exam is important and likely to be assessed, and that you don't mix up polyprotic with amphiprotic, very different meanings. Okay. H3PO4 is only an acid, and it's triprotic. PO4 is only a base, that's also triprotic. Buffer systems, students they're easy to miss, because you won't be told it's a buffer, but Alberta Ed is sort of warning you anytime you have equal amounts of a weak acid and its conjugate base, you're going to have a nearly constant pH. So this might show up, you have 50 mils of 1 mole per liter HF, and you have 45 mils of 1 mole per liter fluoride, maybe sodium fluoride. You'd have to recognize or check your table that they're both weak, and if they're similar molar amounts, you would have a buffer. Now you'd see a spectator ion, not just F-. But just because you have 2 chemicals doesn't make it a buffer. You have NaCl, I don't know, HCl, you've got a salt and a strong acid. That's not a weak pairing, so you would not get a buffer, even if they were in relatively equal molar amounts. You need a weak acid and its conjugate. And these are kind of buried. You may not realize it's a buffer question, but the question is, it's the actual question that's the hint. The question is typically, what will the pH do if you add a few drops of acid or a few drops of base? You see that wording, your brain should be thinking buffer. See what they gave you and analyze it for a buffering system. Okay. There's several ways. Your notes are a bit more detailed about all the ways you can make a buffer. You have to make sure you know the difference between equivalence point and endpoint. Same concept as Chem 20. Endpoint is the color. Equivalence point is that dot that it would have put on a pH curve. Equivalence point is when the curve changes. It's when the moles of the acid is equivalent to the moles of the base. That's equivalence point. Endpoint, you add in an indicator and you get a color change. You need to make sure you don't mix those 2 concepts or those 2 words. And we talked about picking indicators and predicting the colors in your notes. And that sort of wraps up the key parts to the bulletin. Hopefully this helps you prepare for the diploma that's coming up. And you sort of want to study strategically back from, you've got the list of the outcomes in your data booklet, and then you've got these hints to study. I would not study any individual teacher's notes a ton at this point. I would realize what the outcomes are and what the key topics are, because there's lots of little nuances that I or some teacher might have added in, okay? Nuances in labs, okay? But it's big ideas and concepts. Voltaic and electrolytic cells are two big ideas, concepts will be on your diploma. The specific examples I did in my notes are fairly irrelevant and trivial. They're just skill building.